Okay, we're back for the fourth talk in our series about the Earth's biotic enterprise. And today what I want to talk to you about is biogeography, that is where species are located on the planet, and then about extinction and what we know about extinction. So let's get started. We would like to be able to make some general statements about the occurrence of species on Earth. For example, we already have learned about the biogeographic provinces, those regions where there's been a long enough period of isolation in the past to create a distinctive flora and fauna. So what else can we learn about the distribution of species on the globe? Well, one is that for most organisms, there is a latitudinal gradient in which species numbers decrease as you go away from the equators. And here is the number of nesting birds by latitude as you head north. And you can see it drops off from a very high number here, which is the beginning of the wet tropical forest in southern Mexico and northern Guatemala, to a very low number in the tundric above the Arctic Circle. This pattern holds for all sorts of taxa. Here is a latitudinal species gradient for mammals coming from Panama and Central America all the way up once again to the North American Arctic. And here is the latitudinal species gradient for plants. And once again, you can see that same pattern. Around the equator, you get the highest diversity. And you might notice some other interesting patterns as well. So this is a generalized phenomenon that biodiversity decreases as you move away from the poles. Now, the reason for this appears to be that in the tropics, climates are stable, and stable climates allow organisms to live in a narrower niche, in other words, to become more specialized. And a less stable climate does the opposite. Organisms have to remain more generalized. Now, mountains are also areas of high biodiversity, and the reason is related to the change in ecosystems that occurs with latitude. On mountains, it is commonly noted that as you move up in altitude, ecosystems change in a fairly orderly progression, and it resembles the change in ecosystems that occur as one moves away from the equator and towards the pole. So individual ecosystems become isolated. With altitude on mountains, this often allows reproductive isolation and speciation on mountains, but even without that, it allows the packing in of huge amounts of biodiversity on just a single mountain, which has a relatively small land area. Another concept I want you to understand is the concept of endemic species. A species can have a huge range, or it can have a narrow and restricted range with a very limited area. Endemic species are those with a restricted range, especially if it's restricted to a particular geographic area. As a result, endemic species typically have these teeny ranges and are likely to become endangered by humans because they start off with small populations to begin with. Here is a graphic showing where the most endemic fish are, and you can see there are regions that are high in endemic fish, mostly tropical, but also some temperate regions that are high in endemic fish, such as Central Europe here. Certain regions contain exceptional concentrations of plant endemism. So they have been labeled by ecologists as biodiversity hotspots. And many of these areas are being adversely affected by humans. And conservationists believe they have to be conserved to preserve biodiversity on Earth, because these literally seem to be the fonts of biodiversity. A biodiversity hotspot map is shown here. And you can see that the darker orange it gets, the more biodiversity there is and the more endemism there is. And so these are the 35 biodiversity hotspots that were identified originally, and a few more have been added since then. I also want to talk about how islands contribute to biodiversity. And there are two kinds of islands to consider: continental islands versus oceanic islands. So what's the difference between them? Well, continental islands at some point in their recent past have been attached by a land bridge to continents, whereas oceanic islands arose in the middle of the ocean and have never been attached to a continent. Oceanic islands tend to lack terrestrial mammals, amphibians, and freshwater fish, and they're often lacking terrestrial reptiles, but they have birds and insects. And why is that? Well, you've probably figured it out. They are colonized by accidents, and so they're found by organisms with good dispersal power, because these are chance events. And so organisms that have wings have a much higher chance of finding an oceanic island. Oceanic islands also have high levels of endemism because they're highly isolated. They often have radiations or adaptive radiations of species, the evolution of several new species from a recent ancestor. And each one of these new species is adapted to utilize or occupy a vacant niche on this oceanic island. And I'm going to show you some examples of that. And here are the Hawaiian honeycreepers. They are endemic to Hawaii. They are all descended from a single common ancestor, and they have evolved to fill numerous ecological niches that on a continent would be filled by different families of birds. So, for example, this one family contains nectarivores. They subsist mainly on nectar. Frugivores, fruit eaters and seed eaters. Insectivores that glean insects off bark, and insectivores that glean insects off leaves, as well as some generalists. So here, from a single species that reached Hawaii, we now have some 27 species. As an aside, because this will be important later, many of these are already extinct and the rest of them are endangered. Extinction itself is a modern idea. Linnaeus did not even consider extinction as a possibility. When Georges Cuvier, the French paleontologist, proposed it in the late 18th century, and he used as evidence the numerous fossils he found because they looked very different from anything that existed on Earth, most scientists didn't believe him and thought that these organisms still existed somewhere on Earth. We just hadn't discovered them yet. Thomas Jefferson, who had seen fossils, said, "Such is the economy of nature that no instance can be produced of her having permitted any one race of her animals to become extinct, of her having formed any link in her great work so weak as to be broken by extinction." This is an idea that up until the time of Darwin, most people thought was preposterous. There was a creationist ideology where God had made all the organisms on Earth. They were perfect as made, so how could they go extinct? Darwin, with his view of evolution, realized that extinction was a necessary part of evolution. It was a natural occurrence. And it happened for Darwin after a species had been around for a long time and then was outcompeted by better adapted species. We now know that that's not necessarily true. The modern view is that there are two ways to go extinct. First, a lineage can change over time, so one species is replaced by another in time, and that older species is now said to be extinct, but the lineage survives. Secondly, a lineage, a separate evolutionary lineage, can go extinct. It is believed that extinction is a relatively rare event, except that throughout the history of life, there have been periods when a large number of species go extinct relatively quickly. And we want to take a look at these moments of rapid extinction. I'm going to take an aside into geologic time. You have all probably seen a chart of geologic time, and it looks like this, where you have epochs, periods, eras, and eons, eons being the longest, epochs being the shortest. And they're all 3.8 billion years of life crammed into this one table. And if you take a close look at this, you will see that the beginning of one period or the end of another occur at weird dates. And you might ask yourself, why are these dates placed where they are? And it turns out that many of the boundaries are important biologic events. So even though this is called geologic time, the boundaries are often set by biology. The Precambrian, which is this eon right here, is the history of life before there was multicellular life. And this boundary is the evolution of multicellular life. The Proterozoic, so this early period down here, is defined by the transition that occurred to an oxygen-rich atmosphere, and that was carried out by bacteria. And so these boundaries are created by biological events in many cases. Here we have a look at it as a giant junk pile, And you can see the geologic time scale over here, and here are their characteristic fossils. And here we have a time scale over here. One of the most surprising facts that we have learned in the last 40 years is that since the advent of multicellular life, there have been periods of mass extinction. In fact, since multicellular animal life, there have been 5 mass extinctions and multiple other smaller extinction events. All of these define boundaries between periods in the geologic time scale. If we look at this graph, what do you notice? And you can see here that the gray are the number of genera in the fossil record, and the green is the number of well-defined genera, in other words, things that are well known in the fossil record. And what you'll notice is they go up and down in the fossil record. And what this has allowed us to figure out is that these triangles represent periods of mass extinction. And the big 5 are the yellow ones. 1, 2, 3, 4, 5. What else can we learn about these 5 mass extinctions from the fossil record? The first thing is the trend line is for increasing diversity, especially in the last 200 million years, but with sudden periods of biodiversity loss. So left to its own devices, if there's not a cause of a mass extinction event, the planet becomes more biodiverse, but it does so slowly. Second, as I already mentioned, the big extinctions line up with the boundaries of time periods, and here is a listing of the 5 big extinctions and the time periods that they line up with. Third, it takes a very long time to recover from species loss. The estimates of how long it took to recover are for the first 15 million years, for the second 25 million years, for the third 45 million years, for the fourth 5 million years, and for the fifth 10 million years. And the average of those is 20 million years. So it takes quite a while for species loss to be recovered. Here we have another look at the 5 major events, these 2 being close on the heels of each other, this being modern times, and we'll talk about why it has the circle of mass extinction. But here is another important thing to note about mass extinction. When they occurred, lineages that had been very successful for tens of millions, even hundreds of millions of years, were suddenly obliterated from the fossil record. To be one of the big 5 mass extinctions, more than 75% of all the species had to go extinct. The effect had to be global. Many different kinds of species had to go extinct, and it had to occur in a relatively short period, under 1 million years. There is no single cause for all 5, but climate change has been implicated in all of them. We're going to look at 2 of them. The first, the mother of mass extinctions, was the end Permian extinction that occurred 251 million years ago. It's also known as the Great Dying, and I just love that name. It is estimated that 96% of all species on Earth were lost during the Great Dying. It seems to have been caused by volcanic eruptions in Siberia that put CO2 into the atmosphere and bacteria that simultaneously put a huge amount of methane in the atmosphere. And this caused incredibly rapid warming over a 500,000 year period. And as a result, massive climate change and massive extinction, including the loss of all reef-forming corals, by the way. Temperatures soared by 6 degrees, oceans acidified, anaerobic marine bacteria were thought to have produced massive amounts of hydrogen sulfide gas, and this is highly poisonous for terrestrial and marine animals, and so that may have contributed to the Great Dying. Paleontologists say it set life back 300 million years. The major groups that went extinct during this were the trilobites, 96% of the brachiopods, 97% of the ammonites, and several other groups. If you don't know what a trilobite, a brachiopod, or an ammonite is, you might want to go to the Google. The second mass extinction we're going to cover is the one that caused the loss of the dinosaurs, well, at least most of the dinosaurs. And that's the End Cretaceous extinction that occurred 66 million years ago. It is estimated that 76% of all species were lost, It was caused by an asteroid impact and perhaps subsequent volcanic eruptions. The dust clouds that enveloped the Earth sent the temperatures plummeting. The extinction of dinosaurs, except birds, the plesiosaurs, the mosasaurs, the remaining ammonites, and the pterosaurs, occurred during this period. And it's known as the KT event. The story by which it was discovered that an asteroid impact caused the extinction is one of the great pieces of scientific detective work done by a father-son team, about 35 years ago. And this father-son team, when they first proposed this idea, were laughed at in the pages of major scientific journal. But the evidence kept accumulating, and eventually they found the asteroid crater in the bottom of the ocean off the Yucatan Peninsula. And in fact, the oil companies had known about this crater for a long time because they have the best maps of the geology of the Earth because they're always looking for oil. So, that's it for today. Tomorrow, we're going to continue our study of the phenomenon of extinction by first looking at the big lessons from the Great Five, and then going on and looking at the proposal that human beings are causing a sixth mass extinction. And then finally, we're going to go on and consider what it means philosophically for humans to be the agent of the extinction of a large number of species on Earth. Until then, study hard.